Alright, hello class. In this video we're going to look at some advanced techniques. Mainly, maybe advanced isn't the right word, but it's mainly taking all the sort of integration tricks we have already and maybe showing you some ideas of ways that you can apply them in maybe situations you didn't expect necessarily. And I think the best way to go about it is to just start rolling with examples. Alright, and the first technique I want to talk about is what I like to call quick U substitution. You know, there's nothing official about that name. It's just what I like to call it. And the idea is that we want to be able to integrate things faster, right? The faster we can get through some of these things, the better time we're going to have. So we sort of want to speed up the integration process. Okay, and how we do that, I think maybe the best way to show how we go about it is to do it the long way and then kind of give an idea of what it is we're doing, maybe in relation to the chain rule, because U substitution is a reverse chain rule. So if we had this example here, this integral of x squared e to the 5x cubed, okay, this is going to be a U substitution because essentially we have e to the stuff, right? That's what we're always looking for. We're always looking for like e to the stuff, stuff to a power, right? Like sign of stuff, you know, stuff like that. But for U substitution, it can't just be that. It has to be, say, e to the stuff with something close to the derivative of the stuff. I'll just say stuff prime out here, and it's got to be something close. It doesn't have to be exact, but it's got to be really close. In fact, what we would say, us mathematician types, we'd say that they differ by only a constant, okay? Something along those lines. And in this case, we do have a situation like that. We have our stuff here, and remember, our stuff is what we usually let u equal. And then we have some form of the derivative. The approximate derivative is like right here, sitting out front. So let's let u be this 5x cubed, right? And then this du is going to be, well, now we differentiate this and we'll get 15x squared dx. And so what I mean by almost the derivative, or something really close to the derivative out here, is we have this x squared here and we have this x squared here. So these two together, this x squared and this dx, they can come together and be in terms, or put in terms of, say, du. So how you're usually taught to do this in most calculus classes is you divide over this 15, right, and you get, say, 1/15 du is equal to x squared dx. All right, and then we have over here the x squared dx will now be replaced by this 1/15 du in our problem. Okay, and then this e to the 5x cubed, this e to the stuff, that is going to become just e to the u. Okay, so our new integral is going to be, remember this x squared and dx, that becomes 1/15 du, and this e to the stuff becomes e to the u. Okay, then 1/15 du. It doesn't really matter like what order you write these things in. You could also say that this is, say, 1/15 times the integral of e to the u du. You can always take your constants outside. Just don't take u's or other variables outside, right? You can't do that. All right, then from here we just integrate. Again, the e to the stuff, its derivative, or excuse me, its integral is just itself. So the integral of e to the u du is e to the u plus c. And then all we need to do is put our x's back in. So we'll get 1/15 e to the stuff. Now our stuff here was 5x cubed. Okay, so that is your typical U substitution idea. Now how can we speed this up? Well, let's think about if we actually started with y equals 1/15 e to the 5x cubed, and I wanted to differentiate this, say I wanted to take the derivative, the chain rule says that, all right, well, you know, like any derivative or integral, the constant just comes along for the ride. Okay, then now we just differentiate this, the outside, and we leave the inside alone. So by our chain rule, it's going to be derivative of e to the stuff is itself, right? We leave the stuff alone, but we need to make sure that we multiply by the derivative of the inside. So this would be the derivative of the stuff here. All right, and that is going to be 15x squared. All right, and in this case, the 15s cancel, and we are left with, when we simplify this back down, to x squared e to the 5x cubed. Now that is, if we scroll back up a little bit, that is what we started with. Okay, so this U substitution thing does, right, does give us the reverse of a chain rule. Now, something to remember. Remember that integration always reverses the steps of differentiation. Okay, so that's always a very long word to write. So integration is always reversing what differentiation does. So if you think of the power rule you multiply by the exponent out front, then you subtract. So let me just write this out. So if you have x to a power, well, you move the power down, and then you subtract by 1. Right? There's the power rule. But with the integral rule, you do the opposite. Right? You do, instead of subtracting by 1, you add by 1, and then you divide by that value. So it's not even just you go backwards, you do the steps in the reverse order, and you do the opposite operation. So instead of subtracting, you add. Instead of multiplying, you divide. Instead of doing the multiplication first, then the subtraction, you do the addition first, then the division. Right? So integration always reverses your differentiation. Okay? So we can actually use that to help us with quickening up our U substitution stuff. All right, so let's take a look at that. We'll look at the same example, but just to kind of show how it works, and then maybe do a couple others. Okay, so let's actually start with the fact that the chain rule for e to the stuff, if I'm taking the x derivative of e to the u, by the chain rule, that is u prime times e to the u. Okay? So, if the derivative rule multiplies by the derivative of the stuff, okay, then maybe the integral divides by it. Okay, and actually, that is essentially the idea of quick U substitution. Quick U substitution, you basically integrate like normal. So let me write it out like a little algorithm. You integrate like you normally would. But divide by the derivative of the stuff. okay, what you would normally call u. All right, so I'll just say, in other words, u, what would normally be u. Then 2, if all your x junk cancels the way it should, and it's better to just look at an example to see what I mean by that, but if all the x stuff cancels, then it works. Okay, so I think it's easiest to look at an example. Okay, so let's do. Okay, here we're looking at the exact same example that we looked at before, this integral of x squared e to the 5x cubed. Okay, so I'm going to just copy this part down, right? This stuff sitting out front, we actually need that. So we'll just copy that down. Then we're going to integrate this like we normally would. So the integral of e to the stuff is itself. Okay, then I'm just going to divide by the derivative of this stuff. So that's going to be 15x squared. I'll throw in my plus c. And here's where the step 2 comes in. Notice, when we do this, the x squared stuff cancels. Right? And it all cancels. So the x's cancel on the outside. This means it works. So this is crucial to this technique. Okay? So when we rewrite this, you'll notice that I could take that 15 on the bottom out and once again get 1/15 e to the 5x cubed plus c. Now, what I'll say is that, you know, if you don't like this, that's fine. You can always just do a normal U substitution. But I find if you're going to be doing a lot of them, which in this class we will be doing a lot of U substitutions, the faster you can make them, the better. Okay? So what we're essentially doing is integrating like normal, but just dividing by the derivative of the stuff. And if it cancels out the way it should, like here, then it works. Otherwise, it doesn't. Let's look at another example. All right, let's look at this example. This 2 e to the 3x times cosine of 1 plus e to the 3x. All right, so this is an example where I would want to use a U substitution, because what you're looking for is, say, in this case, it's cosine of stuff, so I would want this to be my U. And on the outside here, I have something that is close to a U prime. Right? It's not exactly, but it's close enough, because all we need are these things to cancel. Okay, so what we're going to do is leave the outside stuff alone. Just let that sit. Okay, then we'll work on integrating this cosine part. So I'll do that in a different color here. The integral of cosine, so forget this stuff in here for just a second. Okay, the integral of cosine is sine, so I'm going to do the sine of the stuff. Now remember, leave that inside stuff alone. And then we'll divide by u prime, so the derivative of the stuff. So derivative of 1, of course, is 0. Derivative of e to the 3x is 3e to the 3x. And here's what we need to happen. This e to the 3x and this e to the 3x, they cancel. So it's not just x stuff like all by itself. It can be all sorts of other things. We just need those things to cancel away. Otherwise, it doesn't work. So we still have the 2, we still have the 3. So I'll write this as 2/3. And this will be sine of 1 plus e to the 3x. All right. So let's put our plus c. I probably should have put one up here too. And that will be that. All right, a natural question here is, well, okay, what's an example where it doesn't work? All right, so I've set one up where if we change it just a little bit, it's not going to work. So here, you'll notice all I did was change this out here to an e to the x, not an e to the 3x like we had up here, just an e to the x. So if we actually try this problem, okay, I'll move the 2e to the x out, and then we will try to do our quick U substitution like we did before. So integral of cosine is sine. I'll leave this stuff alone. And then I'll divide by the derivative of the stuff, which of course is 3e to the 3x. But what happens is these don't cancel completely. In fact, what ends up happening is this e to the x will cancel out, but we'll still be left with some of them here because this is essentially e to the x cubed. So what will end up canceling is this. So we'll actually get down to e to the 2x. Okay, which does not work because this comes out to be 2/3 sine of 1 plus e to the 3x all over. Well, we still have some e to the 2x's here. Okay, and if we were to try and differentiate this thing, we would not get back to this thing. Okay, so if we did that, so notice if I differentiate this 2/3 sine of the stuff over e to the 2x, this is well, it's either a chain rule or I could rewrite it to make it a product rule. And I think that's what I might do since it's easy enough to bring that e to the stuff up as e to the negative 2x. Okay, and then do a product rule. Well, notice that what we started with up here is not in the form of a product rule, right? Because using the product rule, you'd get, okay, derivative of the first, so that would be this derivative of sine is cosine. You leave this stuff alone. Okay, now we have to multiply by the derivative of the inside, so we'll get 3e to the 3x. So those 3's there will cancel. We're left with this, so we have e to the negative 2x. So far it doesn't look too bad, right? Because these negative 2x and this 3x, those will cancel to give us this starting point. However, we have another piece, right? We have 2/3. All right, now we leave this part alone, and we take the derivative of the second piece. Well, the second piece, its derivative will be negative 2 e to the negative 2x. Okay, sort of running out of a little room here, but so this does match this, but we got an extra piece. Which isn't good, right? This needs to match exactly if this technique is going to work. So if things don't cancel out, forget about it. You can't do it, okay? But if they do, like here, it should work out just fine because if we were to differentiate this, well, the 2/3 comes along for the ride. Derivative of sine is just cosine of the stuff times the derivative of the stuff, which is 3e to the 3x, and the 3's cancel, and we get right back to where we started with 2 cosine of this stuff times e to the 3x. Those match. Okay, so as long as the stuff out here cancels, like that x junk, it's going to work. If we check out this problem, I call problems like this tricky U substitutions because they don't really look like a U substitution. Usually you need something and its derivative, but we don't really have that. If we let the U be the denominator, we don't get the derivative in the numerator. Okay, but this is where we sort of also solve for U to help us. That's what I call these, the also solve for U cases, essentially. Right? What we'll do, like we can't really set up a quick U substitution here, so I'm going to let U be the denominator, be 1 plus x. Then our du, well, when I differentiate, that's just going to be 1 dx. So actually, du becomes dx, vice versa. So this is just going to be du. Our denominator is going to be u. We need to do something with the numerator. And actually, it may be simpler than you might expect. Here we just solve this for x to get that u minus 1 equals x. And when we do that, that means our x we can replace with a u minus 1. All right, so our new integral here will become u minus 1 on the top, u on the bottom, du. Now you might be thinking, well, what in the world did this actually accomplish? We didn't really, all we did was sort of flip the fraction around, basically. We took a denominator with 2 pieces and a numerator with 1, and then turned it into a fraction where I had 2 pieces on the top and then 1 piece on the bottom. But that is actually what makes this so much nicer, because now I can actually split this fraction up. Right? I can say this is u over u minus 1 over u du. Right? So now this is the integral of 1 minus 1 over u du. And now we can just integrate this. Right? Integral of 1 in terms of u will just be u. Integral of 1 over u, don't forget, that's going to be our natural log, absolute value of u. And we'll throw in our plus c. Okay. Now we just need to make sure we put our x's back in. So remember, our u was 1 plus x. So this will be 1 plus x minus the natural log of the absolute value of 1 plus x plus c. Now here's something you'll probably notice if you look and check your answer and do all that stuff. Books and people will usually rewrite this as just x minus the natural log and the absolute value of 1 plus x plus c. They'll get rid of this 1. And the reason they do that is essentially that, well, we're adding by an arbitrary constant, right? It's just arbitrary. Well, taking an arbitrary constant and then adding it by 1 is still just an arbitrary constant. So they merge constants together to give you just a single constant. Okay. Some people will put a star next to this one, and then when they do c plus 1, they just say that that's c instead. However you want to do it. Grading these by hand, I don't care which one I get. You know, it's not that interesting to me. But when you're looking, like checking your answers and whatnot, do expect to see this behavior here. But what I will say is, of course, we did not have to actually do all of this work. We could have been a little trickier. So what we're going to find out here is a lot of times tricky algebra can save us from doing a lot of extra work. So let's take a look at this example again, but we'll approach it in a different way. Okay, so I have the integral of x over x plus 1. Now, it would be really nice if I had an x plus 1 in the denominator, or excuse me, in the numerator to match the 1 in the denominator, because then I could cancel. Well, the nice thing, and also the not nice thing about math is we can do stuff like that. I could just put a plus 1 in here if I wanted. However, there's a cost of doing business, and that cost is, well, I can't just add the 1 without also subtracting the 1, right? But we can do this. We can add and subtract by the same thing and still have a balanced integral, okay? Now, I can actually split this fraction up as x plus 1 over x plus 1 minus 1 over x plus 1. Now this, of course, just simplifies to 1, and this is minus 1 over x plus 1. Now this, right here, we could do a U substitution, since that's going to be 1 over u case. But if the u is x plus 1, du is dx, There's not a lot of work to do. In fact, turns out that the integral of, say, 1 over x plus any constant a is just going to be the natural log, the absolute value of x plus a, right? Because no extra stuff shows up by doing this U substitution. Now, if there was a number in front of the x, that would change it, but if we're adding by a constant, when you differentiate, it doesn't really do a whole lot for you. So that's another way we can speed up our integrations is, well, integral of 1 is x. Integral of 1 over x plus 1 is natural log absolute value of x plus 1 plus c. Right? And you'll notice we got the same thing that way. Much quicker way of going about it, but maybe a bit trickier. You know, that tends to be the case. If it's quicker, it's often trickier. Okay, here's another one that maybe doesn't quite look like we could do anything with it. All right, because usually for a U substitution, which is really the only real trick we have right now, we need the derivative of the stuff sitting outside of it, and we don't have that here. Okay, but we're going to do a little trick kind of like we did last time. Oh, and that of course should not be x, but I'm going to let the stuff underneath the square root be u. That's often what I try and do is I try and get like the square root of stuff here. I'm going to try, it's usually what I tend to try first, is let's let the u be x plus 1 or 1 plus x. Du in this case would just be dx. And that's still not going to fix this x squared over here. But if we do like we did last time and say, oh, okay, so if u is x plus 1, that makes u minus 1 equal to x, right? I just moved that 1 over. And that also means if I square both sides of this, that u minus 1 all squared is, well, going to be equal to x squared. And there we go. We could actually, and I'm going to go ahead and FOIL this out. That'll be u squared minus 2u plus 1. That will be the same thing as x squared. Okay, so our x squared, we can replace that with this guy right here. So let's do that. Our x squared becomes this thing here, u squared minus 2u plus 1. Our square root of that stuff becomes the square root of u. And actually, to just simplify this a little bit, I'm going to say that that's u to the 1/2. Then, of course, a du, because your dx just becomes du. Okay? Now, this might look worse, all right? But actually, what we've done is we've created a situation where we can just distribute this u to the 1/2 across, okay, and get an integral just in terms of u's, such that we can just use, you know, our normal power rule, right? We've reduced it down to just being a power rule. So let's distribute this through. This will be u to the 2 plus 1/2 minus u to the 1 plus 1/2 plus just u to the 1/2. Okay, so it'll be kind of nasty, but, you know, we do get it to where we want it. So this, of course, is 4/2, so this will be u to the 5/2 minus 2u to the 3/2, since that's 2/2, plus u to the 1/2. Okay, so now we're just going to integrate, and these are all power rules. So this will be u, we'll add 1 to this. So basically we're adding 2 over 2, so we'll get u to the 7/2 over 7/2 minus 2u to, now 3/2 plus 1 will be 5/2 divided by 5/2 plus, then 1/2 plus 1 is 3/2 over 3/2 plus c. Okay, now they're from here, you probably want to simplify. And since we are simplifying, or since we do need to put in the x's back in, we can go ahead and do that at the same time. When you divide by a fraction, of course, that's just the same thing as multiplying by the reciprocal. So this will be 2/7. Our u's are x plus 1. So it'll be 2/7 x plus 1 to the 7/2, right? Minus, when we invert and multiply here, we already have that 2 there, so this will be 4/5. Okay, x plus 1 to the 5/2, right? Plus 2/3 x plus 1 to the 3/2 plus c, and there we go. There's our final answer. All right, a little gross, but it still gives us a way to tackle problems such as this. So if you don't see the derivative, I mean, that's the first sign that you want to do U substitution, but sometimes you'll see stuff like this where you could actually solve, you know, for your x and then replace it with u's and get everything into u's that way. And we'll be looking at problems a lot like this going forward. All right, another sort of advanced technique is what I like to call multiplying by funky ones, or funky versions of ones. Now, you've seen this before in Calculus 1 with limits, and that would be your conjugating factor stuff. So this is similar to the conjugating factors from Calculus 1, because like, for example, if you had some square roots in your limits, so this was for limits, something like, let me throw up a quick example. A limit as x goes to 1 of 1 minus x all over 1 minus the square root of x. So usually if you saw square roots in your limit, what you would do is you would basically multiply by the conjugate. So you would take, say, in this case, I'd change the sign of the middle piece and I'd multiply the top and the bottom by 1 plus square root of x and 1 plus square root of x on the bottom and the top. We'd leave the top alone, okay, to get this is equal to the limit as x goes to 1, so leave that top alone, and then when you distribute this out, so when you FOIL this out, it actually gets rid of all of our square roots, and we actually now have a limit we can deal with. Okay, and we can just plug in the 1 directly now. So it's a similar idea. I'm not saying it's the same thing, okay? Sometimes trying to figure out what to multiply by is a little tricky, but here, again, this is just 1. This is a funky version of 1, right? It's a funky 1, so we can actually apply that to integrals to help us out, right? So in this particular example, I might want to consider a funky 1 because I don't see any way I could set up a U substitution here, right? If I let U be the denominator, the derivative of sine is cosine. I don't see a cosine anywhere, and I don't see a way where I could actually solve like I was doing in some of those other examples where I could solve, get, you know, x or whatever. I've got nothing up here. Okay, so I'm going to try a funky version of 1, and I'm going to try it in the similar style that I did over here with the limit, where let's try actually changing the sign and putting a 1 minus sine theta on the top and a 1 minus sine theta on the bottom, because all we're doing here is, again, multiplying by funky 1. You can always multiply by 1, you can always add by 0, right? These are those things that you can just sort of throw in by magic. And the reason we might want to do that is basically it's called difference of squares. Okay? Now, difference of squares, here, when you multiply something like this out, when you FOIL it out, the middle terms are going to cancel away. right? So this will just be like a review thing here. So sometimes I put in parentheses here so I don't forget that I'm multiplying this entire thing by this entire thing. Okay, but when you say distribute the 1 across, you'll get 1 and then minus sine theta. Okay, then when you distribute the sine across, you'll get plus sine theta minus sine squared theta. Okay, so as we see, the middle terms cancel. So that always happens in situations like this. That's our difference of squares pattern. So the top will still be 1 minus sine theta, and here our denominator is 1 minus sine squared theta, d theta. Now, you might think, well, what have we done here that's actually helped out the integral? It looks worse than where we started, except here. This is our friend, this 1 minus sine squared, because we have the Pythagorean identity from trig, which is definitely one of the ones we need to have ready to go, right? And that is sine squared theta plus cosine squared theta is equal to 1. Now, in this form, it's maybe not helpful, but if we move that sine squared over, you'll get cosine squared theta is equal to 1 minus sine squared theta. Okay, so now, seems to me we could replace this whole thing with just cosine squared now. All right, so I'll get 1 minus sine theta over cosine squared theta. All right, so I think we're almost there, because now we can split up this fraction and get the integral of 1 over cosine squared minus sine over cosine squared. Now you might think, well, how in the world is that actually helpful? Well, turns out 1 over cosine, that should sound familiar, that's secant, so this is secant squared. And then sine squared over cosine squared, well, if I sort of rewrote this like, let me do it in a different color here, say sine, I'm going to split up this fraction via multiplication, say sine over cosine, 1 over cosine. Well, sine over cosine is tangent, 1 over cosine is secant, so this actually becomes secant theta tangent theta, or tangent theta secant theta, and that, both of these are just integral rules, right? So integral of secant is tangent, integral of secant theta tangent theta is secant theta, and there we go. Okay, so what multiplying by a funky 1 did for us here is it actually, with some simplification in algebra, got us down to just rules that we already know. Okay, so that's usually the idea of U substitution or any technique, is to try and get it down to just rules that we already know. All right, so here's another example where we might want to use a funky 1. And why we might want to do that is because if we tried to set up a U substitution in a typical way we would, where, say, we let the denominator be U, we're going to run into some problems. Because if we say that U is e to the x minus 2e to the negative x, our du is going to be e to the x minus another minus, so plus 2e to the negative 2x dx. And that's more than what we actually have. Okay, so we're going to try and use a funky 1 here. And you might think we would use the one or a form of what we've been using previously, like, say, make that a plus and use this e to the x plus 2e to the negative x. We're actually not going to do that here. It seems like it might help, but what we're going to do instead is let me rewrite this problem a little differently. If I say that this is e to the x over e to the x minus, now this e to the negative x, remember a negative x I can bring down and rewrite this as a fraction itself. So this is e to the x over e to the x minus 2 over e to the x. So what we have here is a fraction within a fraction, and I typically don't like those. In fact, I think most people don't. And when you have that, a fraction within a fraction, what you can do is multiply the top and the bottom by the denominator of the fraction that you don't like, or by the smaller fraction. So multiply by I call it a canceling factor. That will cancel the denominator and I'm going to put LOS in parentheses there because it might be more than one, right? But that will cancel the denominators of the many fractions. And this is a trick that actually can be used in a lot of places. It's actually really, really nice to simplify fractions within fractions. So it's a mini fraction that I don't like. Its denominator is e to the x. So what I'm going to do is actually multiply the top and the bottom by that. Okay? Because when you distribute your e to the x across, when you multiply this fraction by it, those e to the x's cancel. Okay, so if I write this out fairly explicitly here, this will be e to the x times e to the x. Right? Down here I have e to the x times e to the x, and then I'll have minus 2 over e to the x times e to the x. So here, those e to the x's cancel. Okay, and it gets rid of our fraction within fraction stuff. Let me make sure my dx stuff is still there. Then, if I think about simplifying this, this is e to the x squared, all squared, which is also known as, when you take something to a power raised to a power, it will be e to the 2x. So I have e to the 2x over e to the 2x minus 2. Okay. And now we can actually set up a U substitution, because if I try a U substitution now, by letting u be the denominator, you get e to the 2x minus 2. Then your du, well, now we'll get 2e to the 2x dx. And we have e to the x, or excuse me, e to the 2x dx in our integrand. The e to the 2x minus 2, that's our denominator. Okay, so all I really need to do is move this 2 over and get that 1/2 du is equal to e to the 2x dx. So over here, this whole thing, this e to the 2x dx will become 1/2 du, and the denominator will become u. Okay, so our new integral is going to be, well, I'm going to bring in that 1/2. I have 1 over u from here, and the du. Okay. So we get 1/2, 1 over u, du. Okay. So from here, the 1/2 comes along for the ride. The 1 over u is a natural log absolute value of u. We throw in our plus c, and now we just put our u's back in. Okay, so we'll get 1/2 natural log absolute value. Our u was e to the 2x minus 2 plus c. And there we go. That's it. Be careful here. The ln's not going to cancel with that e because there's other stuff in here. All right, so often your funky 1 is a conjugating factor, but when that's not going to work, if you've got a fraction within a fraction, try this method instead, because that will usually be your better bet. And the last thing I want to talk about is some obscure algebra. That's what I like to call it. So it's things you learned back probably in pre-cal and thought, and then, you know, you didn't see much again, and you probably thought you'd never use it again. But guess what? When it comes to integration, that's where you'll use it. Okay, one of those is a polynomial division. Okay, now there are probably a few ways we could do this particular problem, but we could also simplify this integral using division. Okay, so if you don't remember how polynomial division works, say you have x squared plus 1 over x minus 1. Actually, I have a video on my YouTube that goes over this with a lot more examples, but if you look in the sort of pre-cal section, you'll find one that's on polynomial division, synthetic division, and whatnot. But if you don't remember that, you can set up a division like you normally would, just like you normally would with numbers. You just have x's and crap instead, right? So the only thing you need to make sure you do is put in zeros for things that are missing. Okay, so since we're dividing x squared plus 1 by x minus 1, I would set up my division like this. X squared plus 0x plus 1 is being divided by x minus 1. Now, I want to know what do I need to multiply this guy by to get an x squared? Well, that's, of course, x. Right? So we multiply this guy by x, and we'll get x squared minus x. And what we want to do is actually subtract this piece. So I'm going to change these signs, right, so that these cancel. That's what I want. I want a 0 here, and then we just deal with what we get here. That 0x plus x gives me a plus x down here. Okay. Then next, I want to know, what do I need to multiply this by to get an x? Before I do that, let me bring this guy down. We could do that later too. It doesn't really matter. But what we need is a 1. Right? If I put in a plus 1, use orange here. Now I'm going to multiply 1 by this term and bring it down here. So we'll just get x minus 1. Okay. Now we want, again, to change the sign here. So we're actually subtracting these. And the x's cancel, and I get 1 plus 1 is 2. And this is your remainder. Okay? So what does that all mean when I put it together? Well, what it means is that x squared plus 1 divided by x minus 1 comes out to be the quotient, x plus 1, okay, plus, it's always the remainder over what you were dividing by. Okay? And that gets this in a format that we can actually, integrate. We can work with this now. Let me actually drop that because I can integrate. Integral of x is 1/2 x squared. Integral of 1 is x. And then this, that's our, since this is just like an x minus 1, we'll get a 2 natural log absolute value of x minus 1 plus c. Okay. Now, it is likely that we could have set up one of those tricky U substitutions here and solve for x as u plus 1 and multiplied it all out and gotten something like, with a U substitution, something like a u squared plus 2u plus 1. We already have a plus 1, so it'd be plus 2 all over u. And do it that way. Okay, So all's not lost if you don't remember this, but for some of you, long division, synthetic division might be a quicker way to simplify the problem to get it down into something more manageable. Okay, the next obscure algebra thing that could potentially help you actually integrate something is our good friend completing the square, which is something that students tend to hate. And I kind of get it, but at the same time, all you're trying to do is force something to be a perfect square. Okay? So here, it doesn't look like this actually will factor, because to factor this, I would need factors of 10, which will be, say, 5 and 2, or, say, -5, -2, or 10 and 1, right? That's an example. That's a possibility. I would need some factors of 10 that would come together to give me -2, and I'm not seeing it. I don't see anything that would help. So we can't actually factor this. So what we would do instead is, since we can't factor it, one thing we can do is, let me look at this. Now this, it would be really nice if we had something that would make this factor. So if I had x squared minus 2x, and I put in a 1, right, that would make this a perfect square. Because now I would want two factors of 1 that would sum up to be -2. Well, I could do -1 and -1. And so that this would factor into x minus 1 times an x minus 1. So that would give us an x minus 1 squared. So putting in a +1 would make this right here a perfect square. So I'm just going to put it there. Right? I'm going to say, all right, that's what I want. So I'm going to put 1 there. I'll just put a +1. So now that this is a perfect square, well, the problem is we can't just throw in a +1 without also balancing it. So you can almost think of this as funky zeros, right? This is basically adding funky zeros, because well, once we add the 1 and then subtract the 1, we've basically done nothing. We made it a 0. Okay? So that makes this a perfect square, which we did over here. So that part becomes an x minus 1 squared. Then we have the -1 plus 10, so that becomes a +9. Now, here's the question. Does this pattern look familiar now? And if not, how about if I let u be x minus 1? And then I said that du was dx. And then I rewrote this integral in terms of u and said it's 1 over u squared plus 9. Hopefully now it's more familiar as a tan inverse pattern. Okay. We have our u squared, we have our 9. So that 9 there means that our a is 3. So we can just integrate this as it'll be 1/3 tan inverse x over 3. Sorry, that's not right. U over 3 plus c. Now we can put our u back in, and our u was equal to x minus 1. So we'll get 1/3 tan inverse x minus 1 all over 3 plus c, and there we go. So sometimes we do have to go back to our more obscure algebra things and use them to help us simplify the junk we're getting in order to integrate. And that should hopefully be enough to get you started. So I will talk to you all next time.